halfway the control, only 400 now. Сразу прыгнул 440 сразу. Huh? Yeah. By Fox. Tony Brown. Сразу на 440. Huh? Because he has too much control. Yeah, inheritance, you know.
Testing.
How you doing?
I'm good. That's still too loud. Let's try that. Better? Too loud? Too soft? Too loud?
Depending on who you ask.
How about this?
That's good.
That's about right? Yeah, I can. I just need a little bit of assistance. That's all. Okay. It is streaming already, so we are ready to go. So sign in. All right. So, are there any questions from last week? Any questions from the discussion of set theory? You know, all the operators related to set theory, or any questions about quantifiers that we talked about, like for all there exists that you're supposed to read? Huh? Yes? Okay. All right. So once I sign in, you know, we can take a look at today's note. So we're going to use quantifiers to re-explain some of the concepts in set theory. You know, so this way, you know, hopefully we can understand both a little bit better, both set theory, you know, all the terms, operators, and stuff like that, and also quantifiers. So before we do that, let me go back to quantifiers a little bit, because last time we talked about the terms, but we did not use the symbols. I don't remember using the symbols. So what we'll do today is to start with that, is to introduce the symbols for quantifiers, because we'll be using these for the rest of the semester. Okay, for the most part, we'll be using a lot of these things over the rest of the semester. So in this part, this notation is saying for all x, p of x. Okay, that's all it's saying. Now remember, p of x is a predicate, and a predicate, once again, is a function that returns a Boolean. In this case, this particular function takes one single parameter, which is x, and x can be anything, because I didn't say x has to be belonging to any particular set before I qualify it with the p, with the predicate. Yes?
What is, I was wondering if you could scroll up a bit, I wanted to write the title of
it. Basic quantifiers?
Yeah, that was it.
Yep, it was in the modules.
Right.
Yep. And that was your reading assignment over the weekend. A really long weekend. Okay. So the other one, that's for all, which is the same thing as every, all in English. And then the other one, over here is called there exists. There exists an x such that, p of x is true. So all that is saying is, in order for this whole statement to be true, all you have to find is one thing, okay, that can make p of x true, then this entire statement is true. Is that okay? What is that thing? Is it an integer? Is it an alphabet? Is it a name? Is it a person? A building? It doesn't say. Okay? It can be anything. All right? So are there any questions about the basic meaning or the notation of for all, which looks like a inverted A? Okay, that's coming from all. Okay, except they don't want to use the regular A because it's confusing. And this one comes from the letter E because it says that exists. Okay, so exists starts with E, but it doesn't want to use the regular E because otherwise that's going to be pretty confusing. All right. So if there are no questions about the for all or there exist operators or quantifiers, then we'll go to here, and we basically want to say, okay, what if we negate the there exists quantifier? Okay, if we negate there exist, that it means, there does not exist one, blah, 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 such that P of X is true. Which is the same thing as saying there's none, okay? Nothing in this entire universe can make P of X true. Okay, we kind of talked about this last week. I said, it is not the case there's at least one thing that can make this true, which is the same thing as saying nothing can make this true. Nothing can make P of X true. So, which is also the same thing as saying, okay, so let me highlight these two. This statement here is really saying exactly the same thing as this statement. So the second statement, if you say it out loud, is saying for all x in the entire universe, it is not the case that P of X is true. But it's really saying the same thing as the first one. The first one is saying nothing in the entire universe can make P of X true, which is the same thing as saying everything in the entire universe makes P of X false. So they mean exactly the same thing. There's no difference between these two other than where the negation is and which quantifier we're using. All right? Are there any questions about these two? Now, sometimes it is useful to move the quantifier in, because as we continue to move the quantifier into P of X and so on and so forth, sometimes we can do simplifications and other type of Boolean algebra to make it easier to understand or to prove theorems. All right. So the next one we want to look at is this one, which is basically saying it is not the case that every x would make P of X true. Is that okay? So the flip side of not the flip side, are you okay? Okay, I'm just making sure that you didn't hurt yourself.
Huh?
Yep, are you okay?
No, I'm fine.
Okay.
What's wrong with these chairs, bro?
Oh. Did it break?
They're like, I'm a sturdy chair.
Okay. Alrighty. So this statement here, which is basically saying it is not the case that everything in the entire universe will make P of X true, is the same thing that to say that there exists at least one thing in the entire universe that will make P of X false. Okay. So are there any questions about the negation involved in quantifiers and how we can move the negation from negating the quantifier to negate whatever the predicate is?
Oh, so it like changes it?
Yeah. So, but when you use something like this, when you move the negation from the outside to the inside, you also have to flip or change the quantifier. So you have to go from a universal quantifier to an existential quantifier. But it kind of makes sense, even just from a kind of casual perspective, the way we use the words, every, none, at least one, and so on. So are we still doing okay so far with this stuff? Okay. So a lot of times, okay, here is the broad statements of nothing and everything. They're not really that useful, but most of the time we want to kind of focus on, let's consider all integers, and we want to talk about integers, or we want to talk about real numbers, we want to talk about two tuples of some kind, and so on and so forth. So in order to quote-unquote filter and just say that this predicate only applies to things inside a particular set, we can use the longhand like this. So we'll take a look at this longhand like this one here, and we'll try to figure out what it means. The for all that is outside of the parentheses is still applying to everything under the sun. Now I really shouldn't say that because there are a lot of stuff that is not under the sun. So this is applying to everything in the entire known universe.
How about the stuff in the unknown universe?
What about the stuff what?
In the unknown universe.
In the unknown universe. Well, everything in the universe, even the unknown. Okay? Conceptual or otherwise. But what we do next is we use an implication. I was about to ask what this symbol stands for, and then I slipped. I'm hoping you guys got what I meant and why it's funny. Because I said, it's an implication. Now, this symbol means implication. So when this symbol means implication, Then let me ask you, what about things that are not in the set X? If I'm considering something that is not in the set X, would it make this entire statement true, false, or we don't know?
We don't know.
Okay, let me ask the question again. This is an implication. If I have something, I'm holding on something that is not an element of X, okay? We know that.
Yeah.
Does that make this entire statement, the highlighted portion, does it make the statement true, false, or we don't know?
It makes it true.
What is the definition of implication? What is the truth table of implication?
It's only if X, then that has to be true.
If the first part, which is called the precedent of the implication, is false, then the entire implication is true. So that means if I'm holding on to something that is not an element of X, it automatically makes that thing is an element of X. That expression itself is false, right? But if the first part of an implication is false, the entire implication is true. Is that okay? If not, okay, there are two things you can do if it is not clear what I just said. One is to reread the first portion of the notes, because when we define the operators in Boolean operators, we define implication. And you might want to look at the truth table of an implication. That's the first thing you can do. But if you read that part already, you have it on your notes, and you know what an implication is, but you still don't know why it would make this entire thing true when I'm considering something that is not an element of X, then you might want to come to my office hour so I can clarify that for you. Okay? What I just said is an implication itself. Remember what I said? If da da la 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 la, then da da da. That by itself is an implication. All right. So what if I'm talking about something that is in X? Okay. What if E is really an element of X? Then just by itself, what can we say about the value of the entire thing? Just knowing that E is an element of X. I'll give you three choices again. The whole thing is true. The whole thing is false, or we don't know yet.
Depends on the second one.
The answer is we don't know yet. Okay? Because if the first part of the implication is true, then it really depends on the second part. If the first part is true and the second part is also true, then the implication itself is true. If the first part is true but the second part is false, that makes the entire implication false. That is a part of the truth table of the implication. Is that okay? Yes? More or less? Okay. I'll give you an example. Okay, there's nothing that can test your understanding better than, let's use an example. And we'll use something that is familiar. And I'm going to use, okay, so we'll have the same set T as we talked about last time. And then we'll say, we got MX5, NSX, and MR2. Okay, there we go. See, of the three, only one is not a production car anymore. The other two are still in production. You guys don't care about that part. That's okay. That's actually good. You're not getting distracted by me. That is good. Okay, so this is set T. So can I? What about a statement like this? Okay, for all E, and then I say E is an element of T, implies. Let me think about it a little bit. Okay. So this one is a little bit, it does depend a little bit on what you know about cars, but I'll tell you that MX5 is rear-wheel drive, NSX is rear-wheel drive, and MR2 is rear-wheel drive. Okay? So now the question is this statement true?
Yeah.
Is it true all the time?
Well, unless you take it
As
down
long-
to a shop and make it a cross-wheel drive.
Okay, so the really interesting part is when we use the word for all, E, we're considering everything potentially as E. In other words, this E here that is outside of the parentheses can bind to a Civic,
Well, Civics,
a Honda Civic, which is known to be front-wheel drive.
Right.
It can also bind to a STI, which is all-wheel drive. It can bind to a motorcycle, which for the most part is one-wheel drive, the rear wheel. It can bind to a unicycle, where you cannot really say, is it really all-wheel drive, front-wheel drive, or rear-wheel drive? I guess you can say all of the above, because it only got one wheel, right? So the one wheel has got to be the front wheel, back wheel, and all wheel. Okay, so that E can be anything. Is that okay? But then the filter is, I got this expression here. So the expression of E is in T is a filter, which is basically saying, if we're talking about the STI, is the STI a part of the set T?
No.
No. So this part is automatically false. E is in T is automatically false. And that automatically makes the entire implication true. Okay? What about the unicycle? Is it in T?
No.
No. So it will make E in T false. That will make the implication true. So we're good. Okay? So let's try another statement. So I'm going to say E is in T implies E is
No, what is the
mid-engine.
Oh, snap.
So once again, we are testing your knowledge of all of these cars, but I'll give you the answer to that part. Okay. So of these three, MR2 is mid-engine. NSX is sort of mid-engine. We'll call it mid-engine.
Okay.
MX5 is not mid-engine.
Yeah, because that's a rotary.
Because it's front wheel. It's a front engine. It's an FR setup. Okay, so we know the MX5 is not a mid-engine, but the other two are. Okay, so what about this entire statement? Can we say that this entire statement is true or false?
False.
It is false. Okay, but how come it is false? Because when E binds to MX5, MX5 is an element of T, is true. But MX5 is mid-engine, is false. True implies false. By that thing is false. Okay, but that thing by itself is false doesn't mean the entire thing is false. That thing is false, making the entire thing false is because of the for all quantifier. Because we are saying for everything in the entire universe, okay, this statement has to be true. But we just found something that is in the set T, and it is also making the second part of the implication false. So that's why the for all itself is false now. So we can now confirm or assert that this entire thing is false. Yes?
Okay, let's say that we do another one instead of cars, like we do one with amphibians, like we have a salmon, a frog, and a salamander, right? And we say that all these are water creatures. We say that E, the element of T, with those three creatures are all considered sea creatures. Would that statement also could you use it in that application as also being true as well?
Okay, so let me write it down. Okay, so we have a set of creatures.
Yes.
Okay, what's in the set of creatures?
Salamanders.
How do you spell salamander?
I don't.
Huh?
Close enough.
Close enough. Okay, but close enough is not good enough in this class.
That's true.
No, you had it right.
Oh
my goodness. It's Mandarin.
You'll find it. Salamander. Okay. What is the second animal?
It would be a frog.
Frog. I can spell that.
And any type of fish of your choice, like a salmon, catfish, or whatever, fresh water, or salmon fish.
Catfish.
Well, it's lunchtime. I'm thinking about salmon.
Okay.
Okay.
So then, if we would say, we'll say all E.
For all,
Yeah,
okay.
for all E, right?
Okay, for all E. Okay.
Equals E element T,
Mm-hmm.
and then
C.
oh C, thank you, and then I forgot the
Oh,
name of the
okay.
arrow sign.
I got it wrong. C.
Yeah.
Okay. Is it implies?
Implies, and then
Uh-huh.
if I could say that all, I mean, and then it's E is sea creatures.
Okay. Well, then it depends on how you define the sea creature.
Exactly. That was my question. That was.
But then it's not a question of the symbols or set theory. It is now a question that is biology. It's a biology question.
Okay.
How do you classify these creatures? So,
Right.
so it's. I cannot give you the answer because I'm not teaching biology.
Sorry. All right.
Yeah, so-
because you was using the car example, and I was trying to see what happens if you run into something like that. Like if you.
Then
run
you
into-
have to ask
Do research.
about the Then you have to ask: is a salamander considered a sea creature? Is a frog considered a sea creature? Pretty sure about false about that one.
Right.
And the salmon is a sea creature.
Right.
Okay, you can actually live in both salty and fresh water.
Right.
Yep.
Okay.
What's funny is that you could have the same example without the fish because the MX-5 is technically mid-engine, in that the center of gravity of the engine is behind the front wheels, but it's a front mount mid-engine.
I think it is still considered a front engine. Most people will still classify it as front
But if you're
engine.
going to classify it technically, the engine is behind the front wheels.
But it's also in front of the
So
driver.
it's front mount mid-engine, and there's rear mount mid-engine, and then there's the NSX, which is just weird. It's fun. And if you're Bentley, you put the engine as far forward as you can.
But that will also make a Mini Cooper also mid-engine. Because the Mini Cooper has the wheels, kind of push all the way out to the extremes. So everything is mid, right?
Well, but Honda's, their engine is actually forward of their transmission, so.
Ah, okay. But I'm in
It's all
for,
this is the technicalities that we're
yes.
getting into.
So in this example, I'm
Gotcha.
classifying the MX-5 as not a mid-engine.
All right.
Okay.
Sorry about that.
Somebody knows
Okay.
cars.
So are we doing okay so far with this?
Right.
Okay. All right. So getting back to the notes. Okay, we can close this salamander one.
Salamanders are adorable.
Okay. So this part is really just continuing to clarify all of those terms that were talked about earlier, but we are also using this shorthand now. So we are basically introducing a shorthand of. Okay, can I answer your questions? No? Okay. All right. So basically, what I'm saying here, okay, with this note here, is I'm introducing a shorthand. So the shorthand looks like this. Okay, switching back to the tablet. Okay, for all E, E is in some set X implies some P of X. Okay, a P of E. So I'm just saying that the shorthand of this is for every E in X. So I'm moving the membership outside of the parentheses, because every single time we use there exists or for all, we really need to specify what set we are talking about. So we might as well just move it outside instead of duplicating stuff in the inside, and then we keep P of E, inside the parentheses like that. So I'm basically saying the first statement is now saying that exactly the same thing as the second statement. They're equivalent. Okay, there are basically two ways of expressing exactly the same thing. Are we doing okay so far with the notation? Okay, so it's just a notational issue, so that we don't have to keep writing something in a long format. All right. Okay, all right. So if there are no questions about this, we are moving on, and we are moving on to the next slide. And here's the next. I'm hoping that it would actually get to the one that I need to access. So we are going back to set theory. We are basically defining the operators, that we have already seen before, but this time using quantifiers. So equality. How do we know that the two sets of X and Y are the same? In other words, X is the same as Y is defined as being equivalent to, if and only if is also known as is equivalent to. Okay. What is the rest? the rest is a conjunction. Okay, so there's a conjunction here. Yep.
Should that be a small letter y?
Yeah, that should be a small y.
Okay.
Yeah, but I can't change my notes now because I turned off my computer at home because they're doing some tree work and they're going to turn off the power anyway. So this is supposed to be a lowercase y, so we'll... And I'm missing something else. Oh, no, it's good. Okay, so we'll take a look at the first statement here first. What is it saying? It's saying for everything, for every e in x, e has to be in y. It is, remember the implicit implication? It has the implicit implication of if e is in x, then e is in y. Okay? The second one, okay, over here, is saying if it is in y, then it has to be in x. So if both of these conditions are true, if something is in x, then it is in y. If something is in y, then it is in x. Then we can say x and y are the same. X being a set, y being a set. Now we can define equality between two sets. Is that okay? So the other way to say that, which is even more concise, is we can say x and y being two sets are exactly the same if and only if give me anything in the entire universe. Okay? But then I have this time not an implication, not a conjunction, but this time we have a if and only if. E is in x if and only if e is in y. If you find me something that's in y, it has to exist in x. If you find me something that does not exist in x, it cannot exist in y. So it's a much more concise definition of equality between two sets. So can this e, can whatever e I pick here be a set all by itself? Yes, it can. Not a problem. Okay? Then you have to recursively evaluate this and apply that to the set e, and so you can check for equality or membership into those sets.
I think you might have an extra parentheses.
Yep, I'm missing a close parenthesis right here.
No, on the top one.
On the top one?
Oh, that's for the one that you're missing one.
Oh, it's missing a parentheses.
Yeah, the bottom one is missing one. The top one looks okay to me.
No, at the end there's an
Yeah,
extra
the end is
one.
extra one.
No, it's not extra.
Oh, the
Yeah,
first one does have
this
it.
one doesn't have the extra one. This one has
Okay,
a missing
gotcha.
one.
Alright. Oh, my bad, my bad.
Never mind.
This is why I don't like infix notation,
Watch that.
because you have to match parentheses.
Oh, gotcha.
Yeah, that's why RPN is good. It's good. Reverse Polish notation.
And but you gotta like learn how to like read that.
It'll take you like 2 days to get used to it, and then you have a whole lifetime to benefit from it. So, all right. So when we have a set description, okay, I hope you guys still remember. E is a set such that an element x, and any element x in E has to satisfy this requirement P of x. Okay, so we talked about this notation before, but now that we have for all, then we can say, oh, that really means exactly the same thing as this. Consider everything in the universe, x. Okay, x is in E if and only if P of x is true. Now remember, if and only if goes in both directions. So what that means, if you can pull one thing out of E, I can tell you right away that P of x is true. If something is not in E, it's outside of E, let's say, whatever is not in E, I can also tell you right away that P of x is false. If you can show me a particular value, okay, so that P of x is true, then I can say that x has to be in E. If you show me a particular value such that P of x is false, I know for sure that that thing is not in E. So it goes in both directions. Is that okay? Yes? No? Because this is defining, it's basically using the operators that we have learned so far, if and only if, set notations, and also quantifiers. It's using all of those things together now. What about the empty set? If S is an empty set, then we know this is for sure. It is not true that you can find something that exists in the empty set. Is that making any sense? The empty set has nothing in it. Now we get into intersection and union. So we can now define intersection and union like this. Consider everything under the sun or everything in the universe for all x. Okay? If x is in the intersection of A and B, then if and only if x is in A and x is in B, it has to be in both sets in order to be in the intersection. But if it is in the intersection, then we know it is in both sets. Is that making any sense? So it is very important to understand why if and only if is important in this case. I'm not using if. I'm not using only if. I'm using if and only if. And union is about the same. So you can see how union, which is defined here, just has a minor difference. I turn the conjunction into a disjunction. And that becomes union. In other words, something is in the union of A and B if and only if it is in at least one of them. It can be in both of them, that's okay, but it has to be in at least one of them. Cartesian product. So the Cartesian product is a little bit kind of clunky, the way we define it here. So we consider everything in A, we consider everything in B, okay? And then we say the two tuple made out of xy has to be an element of the Cartesian product of A times B. And for all xy in A, okay, so this part is this is the entire part of one side of the conjunction. And then the other side of the conjunction says, if you give me some two tuple that is in the Cartesian product of A and B, then I know for sure that the first thing in the two tuple has to be from A, and then the second thing in the two tuple y has to be from B. So it defines the Cartesian product just in a slightly different way. Are we doing okay so far with this? And there's another way to say it too, by the way. There are many ways to say the same thing. Okay, I'll leave it up to you guys to think about. What is the other way to say something? How we define Cartesian product? Subset. Okay, so we're moving on to subset here. A is a subset of B if and only if for every element in A, that element is also found in B. Okay. But what about proper subset of? A is a proper subset of B if and only if A is a subset of B and there exists at least one element in B that is not in A. So B is quote unquote bigger by at least one element. So are we still doing okay so far with all of these definitions and discussions, other than missing parentheses?
Or confusing from missing parentheses.
Well, that one is not too confusing because it's missing the last one.
Oh, that was my part.
Oh. Any questions about this slide? No? This is all good? Okay. All right, so we are moving on. So what we are moving on to now is beyond set theory, which also means now we have a homework assignment on set theory. So the homework assignment is this one. I'm gonna abandon this one. I'm gonna do it right now. So we'll get rid of this one and we'll just remove it. So now we only have this one left. Okay. It is quote unquote a quiz, but it's not really exactly a quiz because you have an entire week to do it.
Okay.
You can open it, work on it, flip-flop between the questions, fix some of the answers. As long as you turn it in or submit it before, I think I set it to noon next Monday, it counts. but it doesn't. Yes, go ahead.
Is there a limited number of attempts or something like that?
One attempt.
Oh.
Yep. So you got one attempt,
It can make
but you
it
have
two.
an entire week.
Can make
No.
it two. Oh.
No, I do not haggle or bargain.
Oh, come on, man. It's just for our self-esteem.
The only way to bargain with me is I can move the deadline up. Make it due on Friday.
I'm about to say, come on, it's for our self-esteem.
No, but you got a whole week. So the whole point is you got a whole week, you read the questions, you read the definitions, you think about it, you read resources other than my notes. Okay, so let's say you say tax notes is not exactly clear. But guess what? Set theory is nothing new. It has existed before computer science.
Well, computer science exists before computers did.
Exactly.
Yeah.
So it's like a quiz, but it's not timed, right?
It is timed in the sense that you have to turn in by
But
noon
it's
time
not
on
like when you
Monday.
open it, it's like, okay, you got an hour to do it.
Exactly. There's
Okay.
no that once you open it, you have until next Monday
Okay.
noon time to turn it in.
So
Yeah.
you can open it, then close it, and then open it again like the next day, and maybe it won't have problems.
Okay, depends on what you mean by closing. If you're submitting, then you don't
Oh,
get
yeah,
a second
But I
chance.
just like exit out of the window.
Yeah, if you just save the answer and just move out, let time out, it will save the answer and it doesn't close it automatically.
So as long as we click the submit button.
Exactly. If you don't click, that button, you'll be fine.
So you mean this button?
Yeah. And it is open book, open notes too, but I would try to do it individually, okay? So I know some of you like to do things together because you learn better together. You can talk about the concepts together, okay? But try not to do the homework together, okay? So that's your homework, over, this entire week, okay? But I would do it as soon as possible because if you have questions about the homework, you can still ask me about it, okay? I'm not going to tell you the answer, but I would point you to the discussion or I will help you clarify the concepts so they can answer the questions. So we are now moving on to this slide here, functions as sets, okay, which is an interesting way of looking at things if you have never seen something like this before. Okay. So when we look at a function, okay, I'm skipping to section 3 right away because the other stuff is kind of, it's not exactly needed here. So when we talk about a function, okay, this is a typical way to define a function. F of x is 2x. It's a very simple function, but nonetheless, it is a function. Okay, from your math perspective, okay. So when we define f of x being 2x, then we can say, oh, f of 2 is 4, f of 1 is 2, f of 16 is 32, and so on. So are we doing okay so far with the first paragraph here? The way we look at functions in general. Okay, cool. So in this class, we look at a function kind of like a map, okay? You give a function a particular value, it maps to something, okay? It can't be the same value, okay? You give it a value, it can map to the same value. It's entirely possible. But it maps it to something else. So that's why, the set, the set of things that can go inside the parentheses is called the domain. The domain is a set. And the values that can be the result of evaluating a function is called the codomain. So we got the domain, we map elements in the domain in elements in the codomain. That's the job of a function. Is that okay? So regarding those two names, domain versus codomain, there are two really important things that you have to remember. You can count at 2.5. The first one is the domain and the codomain are sets. The second one is the direction is from domain to codomain. Okay, we're mapping things from the domain to the codomain. Is that okay in general? Okay. So the notation for that, if x is the domain and y is the codomain of f, so this is a typical way for me and other mathematicians to basically define, not to define, but to describe function f, so that we can now identify that f is a function, its domain is the set x, and its codomain is the set y. Is that okay? Just notation-wise. And you can also see that this is a single arrow, not a double arrow. Because in this class, a double arrow means implication, and I don't want to confuse the use of implication in the function notation. All right? So if we go back to f of x is 2x, now we have to be careful because just like in programming, okay, you have to identify the type of the parameter. If you say the parameter is an integer, then we use this notation. We basically say that f is a function. It maps from the set of integers to the set of integers. Now fx being 2x can also map from real numbers to real numbers, even from complex numbers to complex numbers. But I'm choosing, in this case, to only say that, okay, we are mapping only from integers to integers. Is that concept okay?
Yeah, it's good.
All right,
I'm
cool.
just more confused about this part down here.
This part down here?
Yeah.
Oh, this part down here is really just tedious. Yeah, go ahead.
Oh yeah, so like I know in like C you can like switch between types and stuff like that. So could you also have like mappings from like integers to some other type?
Yeah, you can.
Okay.
Yeah, but in this case, because of
Yeah.
I just choose to use the set of all integers as the code. Okay, so let's move down a little bit to now we are really trying to look at a function as a set now. But it's not really just a regular set. In this case, every element in the set is a 2-tuple. Okay, and in a 2-tuple, the first item is the one coming from the domain. The second item is what does it map to in the codomain. So every single element in a function as a set is a 2-tuple. The first item of the 2-tuple is an element from the domain. The second item in the 2-tuple is what it maps to in the codomain. In other words, this is an extremely tedious way to spell out a function. Okay? So if I want to express f of x is 2x, this is another way to express it, but this time I'm using set notation to define the function, because I'm saying that f itself is a set. Okay, f is a function, but it can also be seen as a set. What does it have? Each element looks like this. Okay, each element looks like a 2-tuple, where there's an x and there's a 2x, and x has to be an integer. So that's basically another way to describe this particular function. But when you look at functions this way, it no longer has to be mathematical. Okay, in a math class, okay, in a calculus class, algebra class, or whatever class you have, linear algebra, and so on and so forth, a function is usually quote unquote mathematically defined. In other words, there's a particular operator that is known to map something from the input to the output, from the domain to the codomain. In this case, that is not the case. Okay, so I can give you a very arbitrary function. Okay, here's an example. So I will say, this is function f. I'm just reusing the letter f here, and it is mapping from the set of ABC to the set of 1, 2, 3. Okay? So at this point, all we know is it is a function. ABC is the domain. 1, 2, 3 is the codomain. And somehow, okay, f is mapping elements in the domain to elements of the codomain. And the actual mapping is now defined by f as a set. I'm spelling out everything in f now. So I can just say A maps to 2, B maps to 1, and C maps to 3. Why?
Question.
No particular reason, but it is a function. Yep.
I was going to say, would it be wrong if I say A in 1, or there was any particular reason why B is 1 and A is 2, or you just...
This is completely arbitrary, which is the point that I want to make.
All right, cool.
Okay? So in this case, f is a function. It has a domain, ABC. It has a codomain, 1, 2, 3, and it is defined. Okay? I know exactly how A is mapped to, what A is mapped to, what B is mapped to, and what C is mapped to. Yep.
Wait, so does the order of A, B, C matter, or can you put like
Nope,
A, C?
it does not matter because it is a set.
Okay.
So, so I can basically say this can also be seen as B1, C3, A2, and so on. Okay, quick question of a future topic. How many ways can I write this? Okay, because the order is not important. So how many ways can I do this? Like, oh, it also equals to this, it also equals to this.
Log 6 or 9?
It is not 9. It is 6 because it is, you got 3 things to choose for your first thing in the list inside the set. Then once that thing is chosen, you got 2 things left. So you only got 2 choices for the second one. Once you have chosen the first and the second, you have no choice because there's only 1 thing left for the third one. So it is 3 times 2 times 1, which is known as 3 factorial. I can list the items inside the set that many ways because ordering is not important. Yep.
You were talking about how many ways could you write f and f and still do that exact same function?
Yes.
I thought you meant how many different ways could you map A, B, C to 1, 2, 3?
Oh, no. Not how many ways we can map ABC to 1 to 3, but how many, given that this is the actual mapping of f, how many ways can we express it by listing the content as elements inside the set? Okay, thank you for that question. It really helps to clarify for the rest of the class. Yep.
So this doesn't work the same as Cartesian product, right?
Ah, good. You made a good point here. Okay, so if you when we move down to section 3.1, then you can see Cartesian product. Very good. Okay, so if you identify that f is a function, x is the domain, and y is the codomain, then we know for sure that f is a subset of, okay, x Cartesian product with y. Does that make sense to you? Because of all the 2 tuples inside the function, the first one has to come from the domain, the second one has to come from the codomain. So it kind of makes sense that it is a subset of x Cartesian product with y. But this is not the only requirement for f to be a function. There's one really tricky additional requirement. So I'm going to skip all this stuff here. Skip. And we'll go all the way down here. Now, if you can read the rest, okay, but I'm going to explain this one and go like, this is a requirement. If f is a function, this has to be true. Okay, so what exactly is it saying? How are you going to read this stuff here? We read from the outside in, okay? So the first part is, okay, let me just highlight the portion. So this part is just saying, okay, this, whatever is in the parentheses, okay, this stuff here, this part here, has to be true for every element in X, which is every element in the domain. Is that okay? You pick anything from the domain, whatever is inside the parentheses has to be true. Is that okay? Okay. So now we focus on the stuff inside the parentheses. So what about this bar thing here? Okay. What does a bar mean in this class? It's a trick question. A single bar doesn't mean a single thing because it comes in pairs. Okay. So now you have to find the ending pair, the ending of this particular bar, which is all the way over here. Okay. So this is a pretty long bar. Okay. What does it mean? The cardinality of, which is the fancy name of saying how many things are in this particular set, right? Okay, that's the cardinality. What set are we talking about? Well, when we use set notation, we use curly braces to indicate the beginning and the end of the list of whatever is inside the set. Okay, so what is in this set here? Everything in this particular set is a 2-tuple. I'll just call the first item in the 2-tuple P, call the second item Q. Okay. Anything special about P or Q? let me describe. P has to be an element. P has to be the same as E. What E are we talking about?
The E that's an X.
The E comes from here. E has to be an element of the domain. Okay? So now we say P, the first item of the two tuple, has to come from the domain. What about Q? Well, Q is restricted here. PQ has to be an element of F. Okay? Okay, fine. And that's it. That defines the whole set. So the set here is really just saying, okay, if you know what E is, okay, it is just looking for all the two tuples that start with E in F. Is that okay? I'll say that one more time. You pick something from the domain. Pick any element from the domain. Okay, here it is. Okay, but that's from X. Then you look at that item and go like, how many items? Okay, give me all the items in F that starts with this thing that is from X. That becomes this particular set. Is that okay? And you don't even care about those individual elements. You are just counting how many items do we have. And the restriction is it has to be 1. Cannot be more than 1, cannot be 0. Has to be exactly 1. Is that okay? So now I'm going to give you certain definitions, certain sets that are not functions. Yep.
How is it actually possible for that to be false
Ooh.
if he doesn't repeat an X?
Well, let me give you examples, okay? Because to make this true is easy, to make it false is, it seems hard, but it's actually not too bad. Okay, so now I defined, okay, so first of all, okay, let me define X first. Okay, so X, which is my domain, is ABC, okay? And Y, which is my codomain, or supposedly my codomain, is 1, 2, 3. Now, they can be the same, but for clarity purposes, it's better to kind of keep them separate and different so that we can look at a particular item and it kind of knows, you know, are we talking about the domain or the codomain? Okay, so at this point, I'm going to just say that F is a set, and it's got A1 and B2, and that's my entire set F. Okay, I didn't say F is a function. Okay, F is really just a set of two tuples. It is a subset of X Cartesian problem with Y. So now the question is, does it satisfy the statement that we were just talking about earlier?
No.
Okay, yes?
So the statement before is more saying it can't be 0.
Cannot be 0. Yeah, because it has to be 1. 0 is not 1. So now we basically look at this and look at the constraint that we talked about a little bit earlier before, which is this one here. Okay, let me scroll this up a little bit. Too much. There we go. And then look at the example. And then I can say F is not a function because it doesn't make this thing true. Why not? Exactly. Somebody mentioned what happens when E is element C? Well, when E is element C, okay, because we have to consider it because we are considering everything in the domain and C is in the domain, right? So when E equals to C, then we go like, okay, what is going to be in this particular set? Remember, this impromptu set is asking for everything in F that starts with a particular value, in this case, C. You look at the definition of F. Does anything in F start with C? No. So that would make the set that we were mentioning earlier, it will make this particular set an empty set. Right? That's okay. An empty set has a cardinality. What is the cardinality of an empty set? 0. So now we say we're comparing 0 to 1. 0 equals 1 is
False.
false. Okay. So that means this thing here is false for at least one item in the domain, which makes f a is a non-function. It cannot be a function because it fails to map one element in the domain to something in the codomain. Is that okay? Another example of something that is not a function.
How to be more than one?
Huh? Oh, that's easy too. How about that?
Wait, how did that happen?
I just changed it. It's okay. It's supposed to be recorded. I'm just checking the OBS. Yep, OBS is still recording. So that's why that's why I said in this class it is important to focus on what I'm saying and not really, copying everything down. You might want to check with me to make sure that it is recording, just to be sure. But when we are talking about this, it is more important to kind of focus on the discussion. Okay, so I'm claiming that this new f, okay, is not a function either. Why is it not a function?
Is a equals 2.
Because a maps to two different things in the codomain, okay? Okay, so, but just to be sure, okay, I just want to show the whole class, what I mean by that. Remember this e here means, for everything in the domain, the rest has to be true, right? Okay. Is a an element of x? A is an element of x? Yes. Okay. So that means this entire thing has to be true for a also. Is that making any sense? This has to be true for element a, because a is in the domain. Okay, so now we look into this whole thing and we ask, okay, so how many pairs in F starts with A? Is 1, is 2. So the set that we were looking at up here has 2 elements. So technically it has 2 elements, A1 and A3. But we don't even care about the membership. We only care about the cardinality. The cardinality in this case is 2. 2 equals 1 is false. So that makes F not a function. Is that okay? And you guys are going to hate this, because the easiest way to qualify a function in this case is to say every element in a domain has to map to one and only one element in the codomain.
Yeah, but in reality, it can be with a different codomain. I mean, this is like mathematically it's correct function.
Hmm?
The f
F right now is not a function.
based on this, based on that thing. But
Based on the
reality,
qualification of what a
something
function is.
can get to about.
Nope,
No.
cannot.
What if a complex one?
Hmm?
Complex function. It's
A
like
complex
give you a
function?
complex value and.
Oh, you don't have to go to complex numbers, because what about the square root?
Yeah, square root one.
It's not a function.
It's not.
Nope. Now, this is a function, but square root is not a function. This is this is only going to give you the positive root of whatever is inside.
The complex number.
Okay, so if you ask a math professor, I can be wrong, okay? So that's why I'm not teaching math. This is 2, but not negative 2. That is the way I understand this symbol. Is that correct? It is finding only the positive root of, or non-negative root of whatever is inside.
The square root
Yeah.
of 4?
But the actual square root is not a function, because there are 2 values corresponding to 4. 2 is a square root, negative 2 is also a square root. So square root is not a function. Huh?
Like the graph being failed with the little test.
The vertical line.
Yeah, it was failed
Yep.
the vertical line test because it goes like that.
Yep.
Oh, so that's what a function is that you're graphing.
Yeah, if you were to graph the should test the vertical line test.
Oh, okay.
and square root does not pass.
Yeah.
Yep.
Okay.
So the definition of function, like this one here, is actually consistent with the math classes. Yep.
But the cube root, on the other hand, would be a function, right?
The cube root would still be a function.
Right,
Yep.
So I have a question like this. If you have f equals the set of a and 1,
Mm-hmm.
b and 2, and then c and 1, will it still be a function?
Well, let's check. So I'm just being lazy here. We're undoing time and do it like this, right? So this is your question. Is f still a function?
Yes.
Well, what do you think?
Yeah.
What is the key to f still being a function? This part here. E is bound to something in x.
The domain.
Yeah, we don't really care what it maps to.
Yeah.
It's just that, does it map to something? How many things does it map to? They can all map to the one thing in the codomain. It's okay. If we have A1, B1, C1, that is still a function. Because it will still satisfy this requirement. Is that okay so far? Yep.
This might be a silly question. What's happening if I decide just to go linear with it, like A1, B2, C3? Would that still be a function?
That is a function too.
Okay,
But
just
it wouldn't be the same as this function.
Okay, just making
Yeah.
sure. Because like if we're talking about graphing, I was wondering.
This would be a parabola.
I was just wondering. So if could you put this on a graph? Like, that's why I said this might be a silly question. Could you put this on like a physical graph?
Not really, because
Okay.
this is discrete. So things that are discrete cannot be graphed, not necessarily.
All right. Yeah, that was.
We also wouldn't
make it
know
like
how to graph it because we don't know if A or B or C is bigger than
Okay. Yes, yes, you can do that. You can visualize the mapping that way.
Like an actual graph.
Exactly, but the difficulty is
graph would be a
um,
line, but because it's a
there's no
square,
line involved
Yeah.
because it's discrete, and then each point is infinitely
Okay,
small,
thank
so you
you.
can't really.
Yeah,
But yes, you can if you want to kind of turn it into a graph. But but then it would be just A, B, C. You only care about the points. That there are no lines involved. I don't have to do it this way either, right? Because I can say C, A, B. There's nothing wrong with this,
Oh.
okay? And in this case, A maps to 1, okay? So there's a dot here. C maps to 1, there's a dot here. B maps to 2, so there's a dot here. But I wouldn't call this a graph.
No.
Okay.
It's just a two-dimensional representation of this. Yeah.
So you more worry about the points, not the lines.
Because each point is an intersection
Right,
from the quote-unquote x-axis, which represents elements of the domain, and mapping to something in the y-axis, which is representing the codomain. So really, it's just another representation of a function. Is that okay?
Yeah, that was it. I was just trying to make sure I was on the same page.
Okay. So, getting back to my notes. Oh, no, that one. Okay. So why is this concept of a function useful? Okay, this is kind of interesting. All right. So I'm not going to read this out. Yep, go ahead.
Sorry, I just had a question. This is going back like kind of a while ago, but I remember you asking about what are the different ways you can order the things in the function, and it ended up being 6, right? But why was that important if it's all the same set anyways? Like, why were we mentioning that, or was it just?
I'm mentioning that because I'm just choosing one of 6 ways of representing membership.
Okay.
And in case people ask me, so how many other ways do we have to represent membership in the same set? I can say, oh, there are 5 more ways to do it.
Okay.
But I'm not going to do it because it's tedious.
Yeah.
Okay, so this part here is basically an example of illustrating why functions kind of arbitrarily defined like this is actually a useful thing. Okay, so forget about the notes. How do you know a sorting algorithm is correct, or how do you know that? How do you verify that an algorithm is actually sorting. So you have an input array, right? And you might even have put the input of how many items are in the array, depending on the programming language. You might have this provided as a separate argument. How do you know the output is sorted? It's the sorted version of the input array. How will you describe that?
And check it yourself.
Okay.
Sensor orders.
All right. So let's give this a try. Okay. It's a very simple question, right? You have a program. Okay. I wrote a program. Okay. You are the one who's going to QC it and go like, okay, the tech mess up and this program doesn't do what it's supposed to. So I wrote an algorithm which is supposed to sort an array, and you are supposed to mathematically describe what a program is supposed to do when it says it's supposed to sort an array.
All the elements from the sorted must come from the non-sorted, and all the elements in order in the sorted one.
Okay. So I'm going to say the input is an array A. Okay. Oh. Okay. So the input is the array A and also n, which is basically the number of elements in A. I'm just going to borrow that cardinality symbol. So now the question is, how do you mathematically define the proper output of this array A when it is sorted?
Can we give the output a name? Can we call the output like the bracket just like...
Well, it might be an in-place sort.
Okay.
So you might need to
Okay.
be able to express it without using a new array. So how would you put it? Now, most people, okay, if you ask someone in cisp 300 or 360, they will say, oh, okay, this is the restriction of the output. Okay, so for the output, we say for all I, that is an element of 0 all the way up to n minus 2. Okay, now there's a reason why it's n minus 2. Just bear with me for now. A bracket I has to be less than or equal to A bracket I plus 1. That describes, the sorting algorithm. But that's not right. Why is this not right? Because if this, yeah, go ahead.
Well, because it doesn't have the first thing that he said, which is that it has to come from the original set.
Okay, so you're absolutely correct, but I can illustrate the incorrect algorithm that will pass this test. Okay? Yep, exactly. You just say for I equals to 0, I is less than n, plus I, A bracket I equals 0. This algorithm will make this, it will satisfy this requirement, wouldn't it? Because when it's done, every single element has a value of 0. Is 0 less than or equal to 0? Does it apply to everything in the array? Is this a sorting algorithm? Okay, so we are obviously missing something. What are we missing? This is a good start, okay? But what we're missing is what you said earlier. Everything in the original array has to be in the output array. But the number of frequency is important as well. In other words, if I have repeated values, like 2 1s and 3 3s and whatnot, the frequencies have to be matching too. You cannot just say, oh, if the input has got 1, 2, and 3, the output is going to have 1, 2, and 3, but the frequencies are wrong. That would not be a good sorting algorithm either, right? So how do you express that everything in the output has to be found in the input, but the frequency has to be right too? Okay, can you feel that we don't have the vocabulary to express that?
Yeah.
And why is that important? Why is it important to realize that we don't even have the vocabulary to express the output of a sorting algorithm correctly? Even though intuitively we know what it is supposed to do, we can spot a wrong sorting algorithm, but we cannot say it. Yep.
Well, I mean, for one thing, set to another set, you couldn't have a frequency of an element more than one. Right?
Okay. So I'm going to give you the answer, but I'll explain that too. Okay. So the answer is to make a conjunction here. Okay. And the second thing is, as the input condition, I'm going to say, a bracket I is ki, and for all I in the set of 0 to n minus 1. Okay. So this is really just defining ki. Okay. Pick a bracket 0. Okay. I define k0 to be whatever a bracket 0 had. Okay, as the input condition. A bracket 1 defines k1. A bracket 2 defines k2 all the way to n minus 1. Is that okay? So in other words, this part here is really just defining the constants k's. Okay, k0 all the way to k subscript n minus 1. So I can refer to those things later. So when I go to this n here, I'm going to express this, okay? It's also in the notes. I just want to point out that it is also in the notes, okay? It's right here, okay? So I'm going to copy that, and then we'll take a look at what I have just copied. Okay. All right. So this is the conclusion. Okay. So here we make use of a function f. Okay. I didn't say f is a function, but it is. F is a function, and not only is f a function. Okay. I forgot one. I used the wrong letter here. F here. And f is bijective. Now we haven't really talked about bijective functions yet. Okay. But this is how we can define that a sorting algorithm is working correctly. Okay, so mathematically, we can say, oh, a subscript I after the sorting algorithm has to equal to k subscript of what is in the subscript of k is f of I. In other words, we are doing a mapping now. Okay? The output, every element in the output as an array has to map to one and only one incoming value from the original array. That part is coming from the bijective. Okay, we're going to talk about bijective in the next lesson, not currently today. But now we can mathematically express the correct outcome of a sorting algorithm. I don't care how it is done. You can have magical creatures inside the computer doing it. You can have transistors doing it. You can have your younger siblings doing it. I don't care. Okay? I just need to know how do I check whether the algorithm is correct or not. Okay? Why is that by itself important? Why do I want mathematical ways to express that a algorithm is correct, the outcome is correct?
Because like maybe the only other way to really do it would be to just test like different like inputs, and there's like infinite number of like inputs though. So if you have a way so that it works for, or like so that you can check for like I guess a variable or like a.
Okay, so that's definitely right. Okay, go ahead.
Before you can have something else check it for you, it has to have like a thing that it can like compare and like see.
Okay, so
if it's actually true.
Exactly. So we want to define what is right. Okay, what is the correct outcome? So the first thing is now we can say we can show this to the developers. Okay, we can show this to the development team and say this is the desired outcome. Okay, so they know what you're expecting. Now, when you say sorting algorithm, yes, most people understand what sorting is. But when you're expressing something else, then it may not be so easy to express using just regular English words, right? But mathematical notations are designed to be concise and precise at the same time. Okay, so that's good. But there's one more thing that is important. Okay, it is a field called automated program verification. So you can look that term up. Automated program verification. It comes in various names too.
What's it called?
Software verification, that's one term. automated program verification, and so on. There are many, many terms to describe the same thing. The bottom line is, you give a particular program two inputs. The first input is the source code of your sorting algorithm. The second input is the mathematical description of what the algorithm is supposed to do. Here's the input, here's the output. Okay? And that program, magical program, is going to crank and crank and crank, and then give you one of two possible answers. Your program works, or your program sucks. Okay? So it's program verification. In other words, what that third program is doing is it is step by step reading the source code of your program and mathematically proving the behavior of your program. So if the derivation all the way to the end of your algorithm, the post condition of the entire thing matches the correct outcome description, then your program is going to work. We do not even need to throw test cases at it because it is now mathematically proven that it's going to work. Okay? If it does not match, then your program is not going to work, at least in some cases. It might work in some cases. It might work in most cases, except for one. But then it still won't work entirely all the time. Okay? Why is that important? See, we are taking several steps back now. We're not looking at the pine needles anymore. What is a pine needle? This is pine needle. Okay? We take a step back out. We go, what is that? We're defining what the sorting algorithm is supposed to do. We take another step out and go like, why do we care? Why do you think we care? Okay, let me ask you, what is meltdown? What is Spectre? Exploits, okay, and they're, to be more specific, they're hardware-specific exploits, okay? But they're exploits, based on software. They're exploits based on hardware. What is common to all of these exploits? Something is not working in certain specific cases. Exactly. Okay, they're doing something other than what we think it should be doing. Okay. Okay, and what is this again? It's specifying what the program is supposed to do, right? So if we can automatically using AI to prove that an algorithm either does do everything that it's supposed to do or not, then we have a way to basically double check to make sure that the code is correct before we publish the code, or the design of the processor, or something along that line. Is that okay?
Yeah.
So which field of computer science do you think this relates to? I would say at least two. Security is definitely one.
And hardware.
Hardware, and there's one more there.
Data management.
AI. Artificial intelligence. Because how do you prove a theorem using a computer? That is artificial intelligence. Okay? It is classified as artificial intelligence. Now this was something that had been done in past decades already. Okay? But it is being picked up again. Why do you think it's getting picked up again? It has several reasons. Okay, let me just remind you when it was hot before. Okay? Automated program verification was a hot topic in the late 70s, early 80s. Compared to now, what has changed?
Faster computers.
We got much faster computers now because of Moore's law. You can actually estimate, okay, what is the order of magnitude of change at this point. So what was not possible before is now like, hey, we can actually do it now. But there's another reason. Back in the 1970s or even 80s, okay, how do we get onto the internet?
Dial I think
you dial up to a BBS, right?
Right.
Okay. So let's say you find a really cool exploit and you can now hack computers.
Yeah.
It's on a floppy disk.
Ooh.
Okay. And what is the fastest way you can replicate an exploit that can only be distributed using floppy disks?
As fast as floppy disk can copy.
Yep. And how fast can you go from one computer to another computer? can it be done automatically?
No.
So somebody has to take that floppy disk, right? To go from one computer to infect the next one, right? But these days, you know, exploits can be spread like that, right? Within a second, okay? If you think about it, okay, an exploit, if it does work, it can spread to thousands, if not hundreds or millions of machines in 1 single second. But back in those days, in 1 second, are you kidding me? You can't even get the exploit on a floppy disk. Then you have to walk over, right? You know, then the exploit has to display on the screen and go like, put this floppy disk into as many computers as possible. And then the person's going to do it. So two things has changed. One is networking. It makes exploits so much more dangerous these days, or so much more costly, okay, these days, compared to like in the late 70s. Two, we have the computation power necessary to do automated theorem proving, which is, you know, doing this sort of thing.
I'm about to say, there's one more factor is how much can the solid or the hard drive, whatever the data is transferred on, and also how much room it can hold the data as well. Like, for example, could the
that has changed too, which also increased the cost of an exploit, right. Because you know in the good old days, your entire hard drive is 10 megabytes. That's like the best hard drive that we have. Okay, it cost me like $700. It's a full height, full length, hard drive. It can also serve as a lethal weapon if you throw it. If you throw it, it's more deadly than a 22. And so now the question is, if my computer got pwned, okay?
Yeah.
How much data can it be? Can someone steal from it? 10 megabytes. Okay.
Oh man.
And then these days, if someone hacked into Google Drive of someone,
But that's too much data. Cause now you get into like exabytes. Like
I don't even bother to get all that data. I will filter it first before I steal it.
Yeah.
Right. So that also increased the risk or the cost of a break-in these days.
Right.
But this is now what people are now starting to use to double check to make sure the programs work correctly, at least crucial parts of an operating system before they publish the code. So they're starting to go back into this area where back in the 80s we go like, we don't care because one, it's too costly, we don't have the computational power to do it, and two, even if my PC is compromised, it's not that bad. Well, that has changed. So this might be one thing that you want to look into if computer security is on your list of things that you want to look into. It's automated program verification.
Never mind, I got it highlighted right here.
So does it check for like holes in it? Any possible loopholes to get into, right?
Possibly, okay, possibly. So you can apply the same technology in a slightly different way. You analyze a piece of code and find out how you can exploit it. Instead of making sure it's correct, now you can actually have an AI to analyze the code and see how you can exploit the code. That is possible as well. But that's also AI and automated reasoning, which is why we have this class. It's not just because we need this class to transfer. As many of you thought, we just need to take this class because we need to transfer. I'll see you guys on Wednesday.